Welcome to today's lesson, Unit 3, Curve Sketching, Lesson 3. We're going to study intervals of concavity today and the second derivative. Okay, so concavity. The graph of a function is concaving up on the interval between random points of A and B if all the tangents on the interval are below the curve. So the graph curves upwards as if wrapping around a point above the curve. Okay, so looking at our little diagram here, we can see that this curve here, okay, this is concaving up. Now the graph of the function is concaving down on the interval of A and B if all the tangents on the interval are above the curve. So the graph curves downwards as if it wraps around a point below the curve. So this is concaving down. So this is just more general term, but basically concaving up, concaving down. Okay, so a point at which the graph changes from being concave up to concave down or vice versa is called an inflection point. So basically an inflection point is a change in concavity. So in the first diagram, as we can see, this is the point of inflection. We have a change from concave down to concave up, and you'll notice in this example here we do have local max and mins. In the second diagram, however, even though we have an inflection point right here and there is a change in concavity, we don't have a definite max and min point. Okay, so we don't have a local max and min or local extrema to be more precise. Okay, so let's go back to our example that we looked at a couple lessons back, where we had a cubic function, okay, and then in red I have the derivative. Okay, so we know the nature of the first derivative and how it relates to the function. Okay, so what we're going to do now is just graph the second derivative. So I take the derivative of the first derivative, which is, I think I've already got a little head start there, which is just 6x. Okay, so we're just going to leave that in black. Okay, let's turn off the original function for just 1 second. So remember that the black one is the derivative of the red one, okay, of the quadratic. And when we have a maximum point, okay, our derivative is then 0, okay, so when it is decreasing, the derivative is negative, and when it's increasing, it is positive, okay. So let's turn off the red and turn on the original function. Let's take a look at what's happening now. So the second derivative in black in relation to the original function, if you notice that the point where we cross the origin, where the second derivative is 0, is where we have an inflection point. Okay, so right there, you notice this part right here, okay, we have a concave down, okay, and then we move along the curve. So let's just leave a little pointer here. No, let's not do that. Okay, so I'm going to move down, so I'm concaving down, and at this point, I begin to concave up, okay? So that, there's our inflection point. So the second derivative at that inflection point is 0. Note that, okay? Because at that point, the first derivative is a maximum, or a minimum, either a max or a min. In this case, it's a minimum. Okay, let's turn that off for a second. Okay, so when we're concaving down, the second derivative is a negative value. When we're concaving up, the second derivative is a positive value. So something just to note. Okay, so and that's our conclusion after studying this graph. So what that means is that we can take the second derivative and use it as a test in order to figure out if the function is concaving up or whether it is concaving down. So what I've done here is summarized everything into a nice table for you. So for instance, if you have your second derivative is positive, okay, then you are concaving up. If your second derivative is negative, you are concaving down. Okay, and if you then find your critical numbers or critical point, you can then classify those critical points as being a maximum or a minimum. Okay, so if both your derivative, if your second derivative is equal to 0, okay, then we have an inflection point. One way that I like to remember this is that if my second derivative is positive, okay, so positive, positive, concave up, smiley face, okay? So if I have a negative second derivative, I have a frowny face. So that helps me to remember. Okay, so when that happens, what I'm going to have is eventually be able to find a local minimum and a local maximum. Okay, right there. Okay. In knowing this, we can also use the second derivative in order to classify critical points. So instead of having to go through points around the critical value or critical point, we can just simply find where the first derivative is equal to 0. And if it fits any of these criteria, then we know whether it's a local max or a min, or an inflection point. So again, if I found the critical number to be a, and I plugged it into the second derivative and found it was positive, okay, I should do this in red, but that's what we've got. Remember, it is concaving up, and that means we have a local minimum. If I found the critical number and plugged it in and found it was negative, the second derivative, then we have concaving down the function, and it is a local maximum. And I just added this little line here too. So if we found a critical point, plugged it in and found that the second derivative was 0, it's most likely an inflection point. Oops. Okay. Pen here, and I'll just draw it. Most likely something like this, which is a saddle. Okay, there we go. Let's take a look at an example. So example number 1, for the function f of x is equal to x to the exponent 4 minus 6x squared minus 5. We want to find the points of inflection and the intervals of concavity. As soon as we see points of inflection and concavity, we know right away that we're going to need to find the second derivative. So the first thing that we should do is find the second derivative and find the points of inflection. And then after that, find the intervals of concavity. So let's take a look at our function. Here we have f, let's rewrite this. F of x is equal to x to the exponent of 4 minus 6x squared minus 5. Okay, so I'm going to go ahead and find the first derivative, which is equal to 4x cubed minus 12x. Okay, first derivative, second derivative. Let's do that again, 12x squared minus 12. Okay, so for an inflection point, we know that the second derivative is equal to 0. That's the criteria. Okay, so let's set this equal to 0. And right away I can see that I can factor out the 12. So I'm going to go ahead and do that. Leaves me with x squared minus 1. Okay, and then I'm going to divide both sides by 12. So what I'm left with is x squared minus 1, and I'm going to solve for the value of x. X then is equal to 1 and negative 1. Okay, so we have inflection points at 1 and negative 1. So in the second part of the same question, we also want to find the intervals of concavity. So we want to use our inflection points as our intervals, okay, so to define our intervals. So we know, we can say that x is equal to negative 1 here, and x is equal to 1. Okay, so we want to actually test values in between those x values. So here we have x then is smaller than 1, okay, and x my mistake, it should be x is greater than 1, of course, okay, and x is then smaller than negative 1. x is then in between 1 and -1. Okay, and we want to use test values. For here, we're going to use -1 and 1, and we'll say this is equal to -2. And of course, my favorite number, we're going to use 0. X is equal to 2. Okay, so when you're picking these numbers for true values, you want to keep it simple. Okay, so let's test our numbers out with the second derivative, because our second derivative is going to tell us, its value is going to tell us whether we're concaving up or concaving down. Remember, we don't actually, it doesn't matter what number it actually is, it's just the sign of the second derivative. Okay, so here we know it's 0. Okay, so an inflection point at that point. So here, if we actually plug this back into our second derivative here, okay, there's our second derivative, -2, so that's a positive, and times 12, it's even more positive, minus 12, it'll still be positive. Okay, so when it's 0, we have x is equal to 0, that goes away, it's a negative. Second derivative is negative. +2, we're going to have a positive value. Okay, we can even take these values, plug it back into our original, and actually find the points of inflection. So in doing so, what we would find, okay, so I'll just do one of them, f of x at -1 is equal to -1 to the exponent 4 minus 6 squared minus 5. Okay, so 1 minus 6 minus 5 is equal to -10. Okay, so at my point of inflection at when x is -1 and my y value is -10, that's my point of inflection. We can do the same here, and what we're going to find, because it's a positive exponent, we'll also have -10. So 1 and 10. Okay, so since it's positive, our second derivative is positive, our function is concaving up. Negative, we have concaving down, concaving up. And remember what I said. Positive, happy face, so concave up. Negative, frowny face. Okay? So finally, what we want to do is to write a therefore statement. Okay, and here I have it down below. Here I've already written it down. So therefore, the function is concave up when x is smaller than -1, when x is greater than 1, and concave down when x is in between -1 and 1. And that would be complete. Okay, so example number 2. Example number 2, we are to sketch a graph of a function that satisfies each set of conditions. So in a part, our second derivative is equal to -2 for all values of x. So the second derivative is negative, so that means that we are concaving down. The second condition says that f primed at -3 is equal to 0, so that will be our critical point, and f at -3 is equal to 9, so that's a point on the graph. Okay, so let's take a look to see how we're actually going to sketch this. Okay. The first thing that we're going to do is I would first sketch the point on the graph. So f at -3 is equal to 9. Okay, so it looks like we're going to run out of room in our y direction. Okay, so at -3, maybe what we'll do in this case is relabel the graph so that we have some space. Okay, so I've done that for you. I've just relabeled it so we have a little bit more room just on the y-axis. Okay, so at -3, y is equal to 9. So I'm just going to put a point there. Okay, so f double primed at x is equal to -2. So we know that it's going to be concaving down for all values of x. Okay, and we know that at -3, we have a local extrema. So in this case, if it's concaving down, it's going to be minimum or maximum value. So it's quadratic. And I'm just going to make a sketch. There we go. Okay, perfect. And that's our sketch. And that would be complete. Okay, so let's take a look at number 2, part B. So f double primed at x is smaller than 0 when x is smaller than -1. Okay, so that means it's negative. So second derivative is negative, which means we're concaving down for the values of x that are smaller than -1. In our second condition, when f double primed at x is greater than 0 when x is greater than -1, means it's positive, so we are concaving up on the other side of -1. So when x is greater than -1. Okay, so our last two conditions here gives us our critical points. Okay, so our critical points are going to occur at -3 and +1. Okay, so the first thing I would do is I'm going to sketch or put a dotted line where my critical points are going to be found. Okay, so I don't exactly know where it is. And again, it's just a sketch, so I'm just going to put a dotted line because I know something happens there. Okay, so at -3, I put my line, and now I'm going to put another dotted line right at 1. Okay, there we go. Perfect. A change in concavity. So I'm just going to put a dotted line there just for now as well. Since when x is smaller than -1, we are concaving down. That means there's going to be a local maxima at -3. I'll do this in another color. Okay, so just to sketch, remember it's just a sketch. It's concaving down with a local maxima at -3. And then we're going to concave up with a local minima at 1. And then remember the function keeps going. For the critical using the second derivative. Our function that we're given is f at x is equal to x cubed minus 3x squared plus 2. So for the function, find the critical points, then classify them using the second derivative. So our first step is to actually find the critical points or the critical number. So let's take the function and find its first derivative. So f primed at x then is equal to 3x squared minus 6x. Okay, so remember for critical point, critical number, this must be satisfied. Okay, so we set that equal to 0. I'm going to factor out a 3x right off the bat, and that'll leave me with x minus 2. So to satisfy this equation, x then is equal to 0 and positive 2. So our critical numbers are then x is equal to 0 and positive 2. And I'm going to set this up in a nice table because it helps me to stay organized. So in the top here, I'm going to put my critical numbers. Okay. And over on the left column, I'm going to have my sign of the second derivative and the sign of actually the behavior of the function itself. Okay. Okay, let's take our values, our critical values, and actually put them into the second derivative so that we can find the sign. Okay, so let's find our second derivative, which is 6x minus 6. Okay, so we're going to now put it into our second derivative, and the sign is going to give us, it's going to tell us whether we have concave up or concave down. Okay, so f double primed at 0 is then equal to -6, so it's a negative number, so we are concaving down. So remember what I had said before, we have negative values for our second derivative, so the function is concaving down, which means we have local maxima. Let's look at x is equal to 2. Okay, I'll put that right in. And that gives us positive 6. So it's a positive, concaving up. So we have a local minimum. Okay, so the final step is that we can actually take our critical numbers and actually put them into the original function, and that'll give us 2 and 2. Okay. What we can do now is write a final statement in order to conclude our question. So therefore, so we have a local max at 0 and positive 2, and a local minimum at 2 and negative 2. And that finishes our question. So one final thing to do today is to check our learning. So below is the graph of f at x. For what values of x is f at x concave down? Make your decision now. And the answer is B. And that's all for today, and we'll see you next time.